I am going to now look at this data that's called Taxi from Chicago in June 7th of 2019. This is every single taxi ride in the city of Chicago on June 7th of 2019. There were over 55,000 taxi rides.
The information they collect is really interesting.
Yeah. Yep. So you get a lot of information. So these are all from these city data portals. If you ever go to like City of Chicago data portal, you find all kinds of interesting information. And every city has them now. All right. So let's look at this data. Just like we looked at the home run data. The variable I'm interested in is the fare, how much people had to pay. Okay. Without a tip. So here we go. So I'm going to look at a histogram of the variable fare. And I may as well make this a relative frequency histogram. And I'll just call this taxi rides on June 7th, 2019. Okay. So there's the graph. And it looks weird, right? You got all these observations right here and then these couple here, right?
Mm-hmm.
Right.
And remember, this is a fare. An $8,000 taxi ride? Holy crap, right? So I think,
Damn.
yeah, I think we should look at these to see what's going down, don't you?
Yeah.
Yes.
All right, so I highlight them. There's 6 observations. Here's the first one. It was a 1-mile trip, and the guy had to pay $6,000. Does that make any sense?
Mm-mm.
He had to pay for the car.
Yeah. So, I mean, odds are sometimes there's data entry errors, and that's what we're looking at right now is more than likely a data entry error. Or here's a trip that was no miles for $1,300. That'll be a data entry error. 0.9 miles for $8,000. Again, data entry error. Data entry error. 1.8 miles, $7,000. Data entry error.
Jesus.
$3,600, no miles, data entry error, right? So I think it's reasonable to get rid of these 6 observations. Something's wrong.
Right.
So I'm going to delete them and then redraw my histogram. Okay, so now my histogram looks like this, and I still have some pretty darn expensive taxi rides. Yes?
Mm-hmm.
Yeah.
So let's have a look-see at these 9 and see if any of them can go away. This was a 77-mile trip, so I believe it being $200.
Mm-hmm.
I'm going to, whoops. So I'm going to leave this one in here. No miles, $250. That's going to get deleted.
Right.
No miles, $415. Delete. 90 miles, $223. I believe that. No miles, $299. Delete. $187, no miles, unless there's a drug deal going on in the back of the car and this guy's paying them off, right? This one, I believe, 99 miles for $235. No tip. That's terrible, but he paid him cash at least. No miles, 173. This one, I believe. And then we're back to that one. So I'm going to get rid of these, and then I think we're good with the clean data. So again, the only reason I'm going over that with you is so that you can see that when you actually deal with real data, it's ugly, messy, and sometimes need to be cleaned up a bit.
Yeah.
Okay. So here's my population data. I'm going to drop this data into that StatCrunch applet. So applet sampling distributions, and we're going to play with the fare variable there. Click compute, and there we can see again, the distribution is highly skewed to the right data, just like it is over here in the histogram. Yes?
Mm-hmm.
Okay. Now this time I didn't compute the mean and the standard deviation on the side, but you can see that the mean of the parent population is 14.5 and the standard deviation is 13.9. See that?
Mm-hmm.
Right here?
Mm-hmm.
Okay. So same gig. Let's take a random sample of size. I'll do a random sample of size 9 and see what happens. Okay. So when I click one time, watch the applet. I'm grabbing 9 rides in the city of Chicago, recording the fare, and then finding the mean. Do this one more time. Randomly sampling 9 cab rides, recording the fare, and then computing the mean. Deal?
Yeah.
Yes.
So now let's do this a lots of times. Here we go. 1,000 more, 1,000 more, 1,000 more, 1,000 more, 1,000 more. So now I have 5,002 taxi rides that I'm sorry, 5,002 samples of size 9 from this parent population. Notice that the mean of all those sample means is pretty close to the mean of the parent population, right?
Mhm.
And the standard deviation of 4.66, guess what? That's close to the 13.9067 divided by the square root of 9. Yep, because that's 4.6 as well. Okay, so those parameters for the mean and the standard deviation of x bar work, even though if you look at this distribution, let me fix this. Clearly, the distribution of x bar is still skewed to the right. Random samples of size n equals 9. Clearly, the distribution of the parent population is skewed right. The distribution of the sample mean is also skewed right, but not as much, right? Not as skewed.
Mm-hmm.
I think it is reasonable to say that the mean of x bar still equals the mean of the parent population, which is about 14.5. The standard deviation of x bar is the standard deviation of the parent population over the square root of the sample size. Because if I do this computation, I'm getting 4.6. So that mean and standard deviation formula works, but the shape thing does not work. So now let's go back here and start increasing my sample size. I'm going to do a sample size, say 25. And I'm just going to do this 5,000 times. 1,000, 2,000, 3,000, 4,000, 5,000. And that's what we get. The shape is still skewed to the right, wouldn't you agree?
Yeah.
But not as much.
Mm-hmm.
And the mean and the standard deviation gig are still playing out. Like if you compute this 13.9 over the square root of 25, I bet it's close to 2.8. Now let's make my sample size, say, 40. 1,000, 2,000, 3,000, 4,000, 5,000. What do you think?
Still a little skewed to the right, but not as much.
The means are still similar.
Yep, all of that is correct. And now if I do this again, but this time, what was this one? 40. Let's say I do 50, a sample size 50. You see how this is becoming more and more bell-shaped?
Mm-hmm.
Yeah.
60. Well, I think this is pretty close to bell-shaped now, wouldn't you?
Yeah.
And so here's the conclusion that we want you to come to in doing all of this. So let me just mark this. This is n equals 40. This is n equals 60. Here's what you want to conclude right here. The mean of the parent population equals the mean of x bar, regardless of the size of the sample. The standard deviation of the sample mean equals sigma over the square root of n, regardless of the sample size. But this item number 2 is humongous. Item number 2 says the shape of the distribution of the sample mean becomes approximately normal as the sample size n increases, regardless of the shape of the parent population. And that idea is known as the central limit theorem. Okay, so the central limit theorem is what is going to allow us to do all kinds of statistical inference in upcoming chapters. It says, regardless of the shape of the underlying population, the sampling distribution of X bar becomes approximately normal as the sample size N increases. And this is also important. How large does N have to be? It really depends on the shape of the underlying parent population. Like here, our parent population is very, very, very skewed to the right. And that's why I needed a large sample size to overcome that skewness.
Mm-hmm.
So you want to make it like bell-shaped then, or?
Well, the more, here, let's do this. Let's say I have a uniform distribution. Okay. Right? Remember, uniform distribution looks like a rectangle. The mean of this is 25, the standard deviation 14.4. I'm going to make my sample size 4. What do you think?
It's,
Pretty bell-shaped.
yeah, it's bell-shaped.
Pretty bell-shaped with a sample size 4. You see that?
Mhm.
Whereas, let's say, oh, here's what's cool about this applet. I can just draw in a curve. I'm just holding down my mouse and drawing in a curve right now.
Oh, cool.
So that's pretty right skewed, wouldn't you say?
Mm-hmm.
Yeah.
Sample size 4, the distribution's skewed right. What if I made my sample size 20?
But the means are still similar.
Yep, the means are still going to work. That always works, right?
Mm-hmm.
But look at, with a sample size 20, it's kind of bell-shaped already.
Right.
You see that? And so that's the moral of the story is you as the researcher, the statistician, have to look at the shape of the parent population and make a judgment as to your sample size based on that shape.
Mm.
Okay? It's like if the shape is skewed like this, you should feel comfortable with 20 or 30 observations, right? But if the shape was like the taxi ride, now you're going to need a much bigger sample size to overcome that skewness.
Mm-hmm.
Ah,
Follow?
yes.
Yes.
So that's the moral of the story there. Sound good? Now,
Mhm.
textbooks tend to have little rules in them. This rule that I'm just showing you that's highlighting in yellow is a general rule of thumb that we invoke, saying the sample size needs to be at least 30, but we just learned that this might not be 100% accurate.
Mhm.
Right.
30 more times than not is enough, but for the super skewed distributions, it's not. So just be mindful of that. Okay.
Mhm.
All right. So now one more example and then we're done. The shape of the distribution of time spent through the drive-through at a fast food chain is skewed right. The mean time spent in the drive-through is known to be 152.5 seconds with a standard deviation of 30.8 seconds. And just so you know, this kind of a problem does exist in the fast food industry. They absolutely want to monitor how much time folks spend in the drive-through, because obviously the more cars they can get through the drive-through in a given amount of time, the more money they make.
Right.
So to obtain probabilities regarding the sample mean using the new normal model, what sample size is required. So this is just alluding to that box in gray, because the distribution of the parent population is skewed right. We need a large sample size, and we'll say we're gonna, because we just said skewed right, not like uber duper skewed right, it probably looks something like this. And so a sample size of 30 is probably legit to make this work. Okay. So again, if the sample size is big enough, you get to say the distribution of X bar is approximately normal. Okay.
Mhm.
Okay. So the quality control manager wishes to use a new delivery system designed to get cars through the drive-through system faster. Like maybe they're going from one window to two. like Wendy's has. A random sample of 50 cars results in a sample mean time spent at the window of 148.7 seconds. What's the probability of obtaining a sample mean of 148.7 seconds or less, assuming the population mean is still 152.5? So the first thing, to answer this question, the first thing we want to do is describe the distribution of X bar. And again, whenever I say describe, you think shape, center, spread. So because the sample size is large, n is 50, which is certainly bigger than 30, the central limit theorem states the distribution of X bar is approximately normal. The mean of X bar is going to equal the mean of the parent population, which is 152.5 seconds. The standard deviation of X bar is the standard deviation of the parent population over the square root of the sample size. So that's 30.8 over the square root of 50. We're going to need that in decimal form for our StatCrunch calculator. So 30.8 over the square root of 50. I'm getting 4.3, I'll write 4.356. And that's also seconds. So visually what we have now is the random variable is now X bar, not X like it was in chapter 7. There's my mean of 152.5. And I'm not going to worry about inflection points and whatnot. My sample mean that I obtained from those 50 drive-through times is 148.7 seconds. So that area right there is the probability X bar is less than 148.7 seconds. Okay. Again, super important you read a random sample of 50 cars as a sample mean. What's the probability the sample mean is 148.7 or less? That's what tells you this is a problem about a sample mean, not an individual value X. So to do this, we go back to our normal calculator. We just said the mean was 152.5. We said the standard deviation was 4.356. And we want the area under the curve to the left of 148.7. Click compute, and there you have it. If we obtained 100 different samples of size n equals 50 cars, and the population mean is 152.5 seconds, we would expect a sample mean of 148.7 seconds or less in what, 19 of the samples, because the probability is 0.1915. You see that?
I see.
Okay. So the observed sample mean is not unusual from a population whose mean is 152.5 seconds. Because the result's not unusual, the system is likely not effective. Bottom line is, it's not at all unusual to get a sample mean of 148.7 seconds from a population whose mean is 152.5 seconds. And so because it's not unusual, it just could have been, you just happened to grab 50 cars that got through the system quickly, right? They didn't order the cheeseburger with no pickles, causing all the cars to slow down. Now, letter C is flip-flopping things. Treat the next 40 cars as a random sample. So that means because it's only 40 cars, now your standard deviation of X bar is 30.8 over the square root of 40, not the square root of 50, because it's 40 cars. See that?
Right.
And so here, and so for this problem, there's your distribution of X bar. The mean is still 152.5 seconds. There's a 10% chance the mean drive-in time will be at or below some value. See how it says at or below? So we don't know what this sample mean is, but because it's a 10% chance, I know that this area has to be 0.10. 10% chance of being at this X bar or less. So for this one, we have to change my standard deviation because I only have 40 cars, not 50. So that's going to be 30.8 divided by the square root of 40. 4.87 if you compute that. So I changed this to 4.87. I don't know the value of X bar, but I do know the area to the left is 0.10. You see that? Now click compute. And there you have it. The value is 146.3. And there's the summary that basically we had two situations here. One, we sampled from a population that was known to be normal, and the other we sampled from a population that was not known to be normal. And the only thing that differs between the two is whether the shape of the distribution of X bar is normal or not. And that all hinges on the sample size.